I'm Adrian and I make toys. And what I want to talk about today is how I made a web-based semi-procedural CAD modeler that saves out 3D printable geometry. So like I said, I make toys. A lot of what I make is for 1/18 scale action figures, and so I make accessories, but I also make diorama pieces. And what I wanted to make was some greebles. So greebles basically means, so this is a really good example from Please Don't Touch Anything. A greebly is just a little bit of tech that kind of makes things more interesting. So I wanted to be able to like fill a whole room, 1/18 scale room, with tech panels full of greeblies. So I made a tool. I made a web-based 3D modeling tool. Let's talk about what it is and how it works. So demo time. Okay, so here we are. This is all running in a browser. I can rotate around. I can drag. I can zoom in and out. All the things you'd expect from a CAD modeler. I can also add semi-procedural parametric details. The way this works is, rather than like going in and modeling in a conventional way, all I have to do is just hold down space and drag a rectangle, and that rectangle is filled in with whatever feature it is that we're adding. So in this case, we're extruding. I'll extrude out a bit more. And I can also set this to negative and extrude in. So I'll make a divot here, let's say. Okay, so that's extrusion. I can also add buttons. So what this will do is it'll add an array of buttons. It'll just fill in that rectangle. I'm going to make them a little taller so you can see them easier. And let's just put a bunch of buttons there. So we've got some buttons. I can also add handles, so sort of like what you'd see in sort of like rack mount equipment. It looks like something that might come out, let's say. And then finally, there's dials. And you'll see we've got this sort of indicator dial with a needle set at a random position. So let's add some more to kind of see how that works. Yeah, so that's the tool. And once I've got something I like, I can hit this export STL and download an STL and then 3D print it. And that gets me something kind of like this. So you can see an example of one of these panels printed out in PLA. So how does that work? So brought to you by ThreeJS. So ThreeJS is a fantastic library. It's been around for years. It's really great. And it does all sorts of stuff. So it's very powerful. And out of the box, you get a lot of great stuff. But there's also add-ons that give you even more great stuff, right? So what I'm using here is there's an orbit controls and there's STL export. So let's actually look at how to make something with that, right? So we're going to do hello world, which is hello cube for 3D, right? I've got some boilerplate. I tried to make it as simple as possible. So at the end of the talk, I'll have a link to the GitHub repo. If you're interested, please go grab it. It's definitely not best practices for JavaScript in 2020, but it is hopefully the most straightforward and easiest to use to kind of jump into this kind of stuff if you want. The key thing here is that all of this is pretty much the whole file. And what is important here is that this MakeGeo function. So we've got this updateGeo function that in turn calls a MakeGeo function. And the MakeGeo function is where all the magic's going to happen. And you'll get something that gives you a render context, lets you use the orbit controls, and gives you a button to export this STL. So let's make some geo. So the easiest way to do it is to just use the built-in, right? So 3JS comes with the box geometry. We can just do that. But that's that's just a mass-produced box, right? For all you wonderful Roguelike Celebration people, we want the artisan, handcrafted, 100% organic box, right? So let's do it the more flexible way. What that's going to mean is in our MakeGeo function, we want to make a new geometry object and add stuff to that, right? So within 3geometry, we just get a blank geometry object and we can put stuff in, right? So let's talk about geometry. So here's our cube, right? Geometry, all 3D geometry is vertices and faces. Vertices first. Right? So here's our cube. We've got 8 unique points. And so let's start by giving them numbers. So we're just going to number them in some order. So here's an ordering. There is certainly a number of different orderings we could have, but you want to do something sensible, right? So for me, I'm kind of thinking of a cube as a flat plane that's been extruded up. And so I've gone clockwise around the bottom face, 0, 1, 2, 3, and clockwise around the top face, 4, 5, 6, 7. So, okay, so we've got an ordering. Now let's actually figure out where those points live. So where are they in 3D space? So what I've done here is I've just kind of assigned, I'm just using 1 for now, But the important thing is that things to the left get a negative x value, and things to the right have a positive x value. And similarly, for front and back for z, and up and down for y. So that gives us a bunch of locations. So cool, we've got an ordering and we've got specific locations. Putting those together, we can add our vertices. So this is what that looks like. So we have our geometry, and a geometry object in 3 has a number of attributes, and one of them is the vertices list, and it's just a straight array. So you can just use it like any other JavaScript array. We can just push stuff to it. And in this case, we want to push vertex data, which is represented with a vector 3, or a 3-dimensional vector. So once we've done that, we've got our 8 vertices, right? So we just do that 8 times. So now we need faces. The key thing about faces is that they don't actually hold any positional data at all. What they do instead is they just reference existing vertices. So that's one thing you have to know about faces. The other thing you have to know about faces is that there's this weird thing where faces only really exist from one side. So if you think about a flat surface in any plane, right, there's something called a normal, which is a line that's perpendicular to that plane. So if you have a flat surface and we have a line that's perpendicular to it, it could point up or it could point down, right? Either one is equally valid for something that's perpendicular to the surface. And that's what's used in computer graphics to kind of indicate which way a face is facing. You can render things double-sided, but it's better if you think of faces as really only existing from one side, because the normals do matter when you go to 3D print. Your slicing software will complain. So trust me, you need to care about it, right? So the way that we specify which side we want, because either side could be valid, is with the order in which we specify faces. So what we need to do is, let's say we're making one of the triangles for our front face. We need to make sure that the indices that we give are given in counterclockwise order. So if we're looking at this from the front, counterclockwise would mean, for example, listing the vertices as 4, 0, 3. That goes around and counterclockwise. If we were to look from the interior of the cube and we had 4, 0, 3, that would be clockwise. Okay, so now we've got sort of all our numbered vertices, and we're ready to actually add them in, right? So let's look at what that looks like. So just like the geometry object has a list of vertices, it also has a list of faces. So we just need to add to that, right? So each face of the cube is, since it's a 4-sided face, we need 2 triangles, right? So we're just going to push that in. And we use this face3 constructor, which takes 3 integers. And because, again, these aren't positional data. They're just indices into the vertices, right? And the vertices are what holds factual positions. And we get a cube. So that's cool and all, but it's a little static, right? So let's get at least some sort of flavor of some proc gen going on, right? So it's not exactly procedural, but at least we'll get some inputs, right? So let's say this is basically the same as what we had before, but it adds in the ability to have an arbitrary size box. So arbitrary dimensions, right? And what I'm doing here is pretty simple, right? I've just got 3 vanilla HTML inputs with IDs for width, height, and depth. I grab the value, I parse it as a float, and then I divide by 2. So what I've done is I just have these placeholder variables, and I have all the same stuff that we had for our original vertices. I just replaced all the ones with the variables for the width, height, and depth. Technically half width, half height, and half depth. And if we do that, we've got this. So here's a simple thing. So this is what's in the GitHub repo, if you want to grab it and play with it yourself. And what we can do is we can change these values and update geometry, and we're back to our 10 by 10 by 10 cube. Or we can make it something like, let's make it kind of flat. And we've got a nice flat surface. So yeah, that's about it. I've got links here. You can grab the repo if you want to play with our little box example. You can play with the greeble modeler online if you'd like to do that. So hopefully after that, the idea of making a web-based 3D modeling tool that makes 3D printable content seems a lot more straightforward than maybe it did at the start. And my hope is that all you lovely people will take all your brilliant proc gen ability and go out and make some really awesome web-based modeling tools and 3D content creation stuff, right? So thanks a lot. Hope you enjoyed it.